Okay, sir. Okay, before starting the session, I would like to introduce Professor R.K Chauhan, sir. Uh, he is presently head of the department in electronics communication engineering in Triple MUT Gorakhpur. He's also my guide also, and he's having a vast research experience, and he's having a number of papers, number of he's also having the transactions also on especially microstrip filter on CMOS devices also. Recently, he had a patent on the tapered CMOS device also. Recently, he got a patent on the tapered body reduced source CMOS structure, and he's also having with his papers in filtering antennas. Then what must I say? He's also my guide. Also, I had done my PhD under him, and speaking no more. Already, time is being is going on, and I should must like to request Professor R.K Chauhan sir to please go ahead with your session, sir. Sir, please, sir.
Okay, thank you, Dr. Yatin.
Thank you, sir.
Uh,
Yes, sir.
uh, One of my area in which my students are doing what I can say is I will be considering that topic for this presentation. So the logic behind considering this topic was also that during one of our examination in the current MTech presentation, I found that most of the students are unaware of how the development of semiconductor industry has taken place, and in context with the projection that has been done by the international agencies, how the development has taken, and is that the development has gone in the same direction or not. That was one of the key
Right.
questions, and what we found that students were not aware of that. So I thought that the topic should be such that uh, everyone will enjoy, and one should know how the semiconductor industry projection was done by the international agencies, and thereafter in India also what steps we are following related to it. So semiconductor, everyone knows that first semiconductor came in 1947 around, where Bardeen and other has done some work. After that, lot of research was going on related to the germanium, because first transistor or first diode or first device was germanium based. Thereafter, research related to the silicon base started, but it was the Gordon Moore in 1965 who firstly predicted something related to the development of semiconductor device, that how it will grow. And it was one can imagine that in 1965 the type of prediction he has done, and we followed up till around 30 years of time. And before 95 or 98, one can say that every prediction that he has done was up to the mark. There was no doubt in it. Initially, he predicted that the number of transistors will get double in 10 years' time. And what he found in 1975, that the pace of research was going at such a rate that the number of transistors was getting double in less than what he has assumed. And thereafter, he predicted it for 2 years, that number of transistors will double every 2 years from 75 onwards. But finally, what we found in our book is that it doubles in around 18 months. So that is what has been finally concluded from his comment. And we have seen how the whole development in this particular device has taken place, semiconductor device. This was something related to. And
Excuse me,
what
sir.
was the major reason for
Excuse
it?
me, sir. Sir, your slide is not visible, sir.
Yeah, it is visible or not?
No, sir, it is not visible, sir.
Okay. So should I, your first slide, this was visible?
Yes, first slide was visible, but after that it was not visible, sir.
This one?
The first one, sir. The that is semiconductor evolution of semiconductor something industry.
Okay.
That was visible, sir.
So this one is not visible.
No, sir.
Now I am showing at least fourth slide actually.
I was trying to stop you, sir, but I
So
did
should I
stop, sir.
connect once again
Yes,
if there is
no,
any
sir.
issue?
You can continue from the fourth slide only, but before that, we must go ahead with the presentation on whether the slide is presented here on the network, sir.
I am just trying to share it once again.
Yes, sir. Yes, sir. Now it is visible, sir. Now your screen is visible now.
Is it visible now?
Yes, it is visible now, sir.
Okay. So I was on this slide.
Yes, sir. Impact of Moore's law.
Should I continue?
Yes, sir. You may continue, sir.
Okay. So the impact which has been of Moore's law in the field of semiconductor was that is device dimension every time it shrinks and cost per function decreases, and it was estimated to be 35% per year at that time, and power per function also decreases, and speed where increases. So those who are working since 1990, they can easily understand the whole development that has taken place with respect to the speed of your processor and the memory space that has increases vast during this period, during the growth of this computer. If we see the size, corresponding size of the transistor which we are facing at present, 1 micron is, you can imagine that it is nearly your bacteria size, and 100 nanometer is your virus, and protein is around 10 nanometer, and your DNA is 1 nanometer. And what you know is your dual core processor or core 2 duo processor that were used in 2003 and 2007 around, the Intel which was manufacturing was around 45 nanometer at that time. But the size which currently we are using is around 10 to 12 nanometer. So you can imagine that we are already moving towards the size of the DNA. So further reduction in this device dimension is not going to be a easy job. And the whole development that has taken place in the reduction of the size, one of the key component was the design of CMOS circuit. Because simple MOS, if we see the growth of MOS around late 60s, that means from 67 to 71, if one go into the literature of MOS, they will found that suddenly everyone in at the international level, they thought that the device or the circuit cannot be designed using MOS. Reason was that a space satellite was sent at that time by US, and it suddenly stops working. And later on, when study went into the failure of that mission, they found that it was the device which was responsible for the failure. Sudden power failure was there, and the reason was ionizing radiation at that time. And no one predicted that radiation can damage. Initially, it was assumed that MOS consisted of metal, oxide, and semiconductor. That means one oxide layer is there and which will be less affected by any radiations, because insulating layer is there between metal and semiconductor. Because of this, people thought that your MOS will be more safer, and they designed the satellite according to that. And suddenly, when failure took place all over world, the research start going on. What was the reason? And the reason thereafter came that it was the oxide which was mainly responsible for the failure of the device. And not only if we see the effect in oxide because of the radiation, we find that the two effects are there. That means trapped charges in the oxide, and another is the interface trapped charges between the oxide and semiconductor layer. These two oxide charges and trapped charges, they constitute major failure for the device when radiation is very high. When we see the dimension for the larger dimension, initially it was the oxide trapped charges, but with the reduction in the size in the late 90s, it was found that it was the interface trapped charges that is causing the major issue in the device application. So from 75 onwards, when people started working effectively on CMOS, and low power application increases, so the CMOS came into existence because of its special feature that static noise margin was ideally almost zero, and the device dimension was decreasing continuously, and the power supply that was required for that CMOS was also very low. If we see the timeline, the how the growth planar process, when it came into 1958, that was the major reason for the growth of the integrated circuit. And after that, it was the first step was the Moore's law, who started predicting about the future of semiconductor. And commercialization of MOS, as I have said, that it started in 1969, but from 71, when reason of failure and other considerations were taken into effect, commercialization of MOS has taken place. Then the Moore's law has predicted once again in 1975, which is now more or less available in every textbook, the type of prediction he has done. And if we see the type of scaling that is being taught in every institute is geometrical scaling, which was effected from 1975 and it went up to 2002. Thereafter, we have seen in the growth of the industry, semiconductor industry, that the scaling was not so important, and the other effect were also necessary to take into effect. So equivalent scaling was the term which is being used, and continuously the type of growth. If we see the 3 days back article from Intel, which predicted that even 3 nanometer transistor they have prepared, and they wishes to introduce into the market also. And finally, the prediction is that it will be the 3D power scaling from 2025 onwards. There is another timeline too, which we say that from 1975, when Morse has came into that every 18 month or every 2 year, the device dimension will decrease, and your size will acquire more number of transistors. So at that time, the oxide thickness was around 250 nanometer, because whenever we do the scaling or we do the decrease in the size of the transistor, what we find is that uh, as we go on decreasing the channel length, you have to decrease the oxide also, so as to maintain the current behavior, so as to acquire the same type of current behavior. Then only the scaling purpose is solved. So from 1975, when you were having 20 micron dimension, and when we reaches up to 80, 85, we found that the dimension has gone to the 5 micron. And from 1990 onwards, when you have seen that your oxide thickness has gone to the 50 nanometer, or you can say 150 angstrom. So people started thinking now what to do when continuous shrinkage of channel length will go there, because oxide thickness, everyone know that less than 50 angstrom, you have a hot carrier effects and degradation in the oxide trapped charges, and interface both will going to trouble you. And short channel effect, as you can see in the slide right side, that short channel effect, because of that, is going to increase from 1995 onwards. And thereafter, international agencies started working all over the world. So how to predict what type of development will take place in the semiconductor industry? Will there be a saturation in it, or semiconductor industry growth in semiconductor is going to stop? So for that, international organizations were made, so as to predict how growth will take place and how the whole world has to approach towards semiconductor industry, so that its continuous development do not stops. From there, the concept of roadmap started, because earlier it was the solely effort of Gordon Moore and the lab, which we are predicting that the device dimension will decrease and the whole industry will go ahead. But from 1991, when agencies start thinking that there should be a common consensus between uh, all the organization, you can say those who were working in the development of semiconductor, that the roadmap should be there, and on that roadmap the investment it can be done. So the purpose was to improve the link between academia and industry. The first foremost aim for this formation of this roadmap was to develop a continuous link between academia and industry, so that the future can be predicted, and industry can go ahead according to that. And if we start predicting properly, then only you can stimulate investment also. And if we try to link what I am saying and what has happened in the back in the 1990s and 2000, you can easily correlate it with the development of Kodak. If everyone remembers what happened to the Kodak industry, because we all have used Kodak camera in the 1990s, and at that time it was the topmost technology for this photography. But what happens that they were solely devoted to the analog photography, and they never tried to move ahead, as the semiconductor industry was proposing various type of technology for that purpose. And what happens to that, that after 1990, in 2000, everyone has seen that Kodak industry is out of picture. So whenever you are going for any high tech sector, it is necessary that everyone should see the projection of the society which is preferring the, because digital was going into the development in 1990s, and everyone was expecting that analog, most of the analog devices will be replaced by these digital devices because of the CMOS and growth in MOS technology. And secondly, what we can see is, if we one remembers the Thomas Cook also, this industry was all over world since in 1880 onwards. If we see, Thomas Cook was dominating in the field of travel, tour and travel, and suddenly it was also bankrupt in the late 2000, when people found that all these internet bookings and use of technology for tour and travel increases, the physical offices and the physical working was not at all desired. Same one can understand with the use of Ola, that how it has impacted after 2013-14, that your taxi and other bookings that was done through Ola rather than physical booking of taxis were there. So whenever a high-tech sector is coming into the picture, one has to see the type of projection that is going on, and one has to update it according to that. And this updation also motivate investment also. That is why the whole concept of this today's presentation was that how we should always try to see the projection that has been done in the field of semiconductor, and how we should go ahead in the academia also, so that our industry get benefited, and the growth of semiconductor is continuously taking in the same pace that has been done in the last 2 or 3 decades, we can say. So another is, it provide elements for future research programs and activities to coordinate efforts and propose most promising solution. If we see the type of solution that we are getting in the banking sector especially, earlier no one was thinking that these banks will go online, and most of your work will be done either through your laptop or through your mobile phones. So the type of solution that has been provided through digital mode. Similarly, if you see the type of the concept, the cryptocurrency or Bitcoin that is coming into the picture, no one is expecting what type of growth it is going to take place in the future. Even government, or you can say all over the world, no government is going to take effective measure, because they are not at all understanding the type of growth that will take place if cryptocurrency or Bitcoin came into the picture. So it has to see, because no one can stop the growth in the technology high-tech sectors. So one has to cope up with the continuous effort that is going on in this particular. So various road mapping activities were performed, we can say, in 1991 onwards. And in the US, it was the National Technology Roadmap for Semiconductor was formed, and they started predicting. Similarly, if we see in the Japan, it was the System and Device Roadmap of Japan that were helping Japanese industry to grow according to their prediction. And in Europe also, it was the organization NARED. But in 1998, when the dimension was at a very low level, and short channel effect of the device was affecting the growth of the transistor, the performance was degrading. At that time, it was felt that all over world the ITRS should be formed, and with the help of Japan, Taiwan, Korea, all these organizations, they started working in a same manner, and they start thinking of what to do. So ITRS, one can say that it is the next generation for projecting the growth of semiconductor. And IRDS, which is currently, it is the third generation organization which is predicting the growth of devices and system. Main aim of ITRS, as we see that it was it started in 1998, but it ended in 2015. And at that time, the main purpose was to synchronize technological development and the availability of equipment so that you can face the critical challenges. So from 1991 to 97, it was NTRS, and the focus was only the shrinking of the device. And thereafter, you started thinking how differently when we can do the device scaling. So ITRS was basically the second phase, and in during this phase, uh, engineers, scientists, and researchers, they found that not only the dimension, but we have to see the material also. We see the architecture of the transistor also, and in that regard, lot of new material came into the existence so that you can cope up with the problems that has been faced because of the short channel. And in this regard, high K was being used. In 2003, it was hafnium which came into the picture, and lot of other material. If you see the dielectric constant of hafnium oxide, it was more than 20, and whereas your SiO2, it was around 3.9. So initially, people started with the silicon nitride, and being a silicon material, it was quite helpful in the providing insulation, as well as using the same silicon material so that your IC fabrication is not a complex issue, because once you use a different material, your lattice constant, your lattice disturbance, lattice vibration, it starts, and your efficiency of the device goes down. So people started with the silicon nitride, but later on, when the device dimension was needed at lower, around 15 to 20 nanometer dimension, then you go for this hafnium oxide and latmium oxide and titanium oxide, etc. Another term which was being popular when you ITRS was abandoned, that now this organization cannot predict because of the shrinkage of the size of the transistor. So more and more than more, these two terminologies were there. What we have found that continuously more prediction was there for device decrease, but later on, people started thinking that if we go for more production, we are not going to achieve the growth of semiconductor industry. So more than more, the concept of more than more started thinking, and people started working on how the device can be used differently for making the chip, etc. So silicon on chip and silicon interface package, so this or system in package, these all terms now came into there were more significance, and people started application based ICs. So ASIC came into the picture so that the growth will continuously be there. And now beyond CMOS also, people were thinking, because simply CMOS devices is not going to serve the purpose. So more this terminology, which simply speaks of shrinking of physical sizes and digital functionality to improve the density and performance, whereas more than more is functional diversification. That means you were not at all interested in simply shrinking the device dimension, but we are more focused towards the architecture also, and a lot of functionality has to increase so that you go for the growth of the semiconductor. And that is why the term SIP, that means system board level into the packages, and system package on chip. this is another way of expressing more and more than more, which may create interest in the audience. That more was simply useful in computing and data storage, and whereas more than more, we are focusing on the devices application in the various field, not only as a sense, interact, empower, and system on chip, system in package, etc. Another way of representing more and more than more is related when you are focusing. The red part is related to the more, whereas blue discusses more than more. That means you are going for a functional uh, variability. So after 2015, when people started thinking beyond shrinkage of the device, so a lot of development in the field to increase the power performance area, and now data mobility, cloud, etc., was growth in this particular field was going to take place. And if we see from 2013-14 onwards, instead of CMOS, we were shifting towards FinFET, and currently most of the devices are FinFET based. Simply gate all around devices also came into the picture. So future was now not on only MOS or CMOS, but beyond CMOS we were moving, and extending the functionality of the CMOS platform via heterogeneous integration of new technologies. We were moving and stimulating invention of new information processing paradigm. So, lot of transistors. If you see from the 2010 onwards, you will find researchers doing in the field of single electron transistors. Some of them are working in quantum dots. Spintronics was also one of the popular term, although it does not uh, go ahead because of the reliability concern. But nano ribbon technology and carbon nanotube, they are to be the look into the future. And it is expected that because nano ribbon has been, we have seen that a lot of research is going on to develop the device or device design using nano ribbons. We can see the prediction of ITRS or IRDS, what you can say currently, that we will go towards 3 nanometer. As I have said, around 2-3 days back, Intel has proposed 3 nanometer device technology node to be used for your devices. Although a lot of issues are there, Intel has said that it may not be used in the industry in the current format, but they are expecting to be by the end of this year. They may be using with some modification for this particular. So what we have seen from 1991, that we started from NTRS, then we have shifted to the second generation of ITRS, ITRS 2.0, and then finally currently it is the IRDS, which is predicting the whole, because now it is not a roadmap for semiconductor, but it is now important. The whole ecosystem requires your semiconductor. And we have seen in the last 6 months also that our automation industry, Maruti has proposed that there is a shortage of the electronic component. That is why they are not able to supply the vehicles, those who have gone for the booking of the automation, this vehicle, four-wheeler. So they found that the shortage of semiconductor is heavily seen all over the world. So whatever the prediction of IRDS was from 2013-14 onwards, we have found that the growth of semiconductor is moving in the same manner. And they have predicted that in the coming 15 years, the whole growth will not only be limited towards the semiconductor which is used in the electronics devices and circuit, but it will go to the system. And your system will be your Wi-Fi station. It can be mobile phone, it can be a vehicle. So a lot of diversification will be observed in the, and only then you can assume their semiconductor industry to grow. And if we see the role of artificial intelligence, the way this particular branch is going on, and IoT, the type of growth is seen in the field of IoT. One can easily predict whatever IRDS has predicted. The device is semiconductor growth of semiconductor is going to take place in the same manner. The second part of my speech is focusing some on semiconductor materials, because what I have seen that uh, the focus which was there in the first 3 decades was only on the silicon. But later on, from if we see the when ITRS 2 was there, they predicted that we should now move towards other semiconductor material also if we wish to have a growth in the semiconductor industry. And if we see, initially it was the stressed silicon which was used, and not only the semiconductor material, but we started functioning on the various types of metal also, so as to maintain the your current equation and your gate technology. Because earlier the gate were prepared by your aluminum metal, but in from 1998 onwards, if we see the growth of MOSFET, we find that instead of aluminum, it was the polysilicon, and thereafter it was the silicide. That means polysilicon doped with refractory metals. Lot of refractory metals were researched, and they have been using for this formation of metal in case of metal oxide semiconductor for MOS. So traditionally it was aluminum, but now no one is using aluminum or polysilicon, simple polysilicon as a gate metal. So in the growth of gate also changes, and from single gate to double gate and thereafter to FinFET, we have seen how the growth of fin is going to affect the current behavior. So not only the metal but also the semiconductor material. That means initially when it started with the straight silicon, in that they for increasing the mobility, some germanium was incorporated. Thereafter a layer of your graphene was used, and similarly the growth of gallium nitride and other indium gallium nitride. These semiconductor materials were also being used effectively from 2000 onwards. And that is why you will find that the LED industry, which came into existence only in 2000, and you will find that most of your bulbs are replaced with the LEDs from 2015 onwards, because growth of indium gallium nitride has taken in such a manner that it has totally replaced the earlier devices or earlier your material used for optoelectronic purposes. So the semiconductor material also, role of semiconductor material also becomes significant. And if we see the automation of the industry, we will find that high power was required from the semiconductor side. Earlier, what we know about the semiconductor, that it was a low power devices. It was good for low power devices. That is why your memory, your processor, all these were used. But when you started having a large power requirement, especially in automation industry, automobile industry, so or driving high power transmitter, then you require wide band gap materials, because low band gap material were not going to serve the purpose. It allows power electronic component to be smaller, faster, and more reliable. Your main aim was to have a material which can serve the purpose. That means it is a smaller but it is a faster and more reliable also. So, with the usage of wide bandgap semiconductor, your electric vehicle, fuel cells, all these started. This is also a slide. If you see the behavior of silicon carbide, which is effectively used in the industry for high power application. Uh, it is not at the research level, but it is in the usage in the industry. Although gallium oxide is still at the academic level, and it is now, we expect that in the coming 2-3 years, we will move towards the industry usage of this gallium oxide. So if we see this graph, we find that the thermal conductivity of silicon carbide, that means the black part, that is very good and quite high. And because of this, you are using this in a high voltage engineering or high power requirement industry or high power transmitters, etc. Although electron mobility in silicon carbide is less, because in gallium nitride, if you see the red part of this, you will find that the electric field is high critical electric field you can achieve in the gallium oxide, but your thermal conductivity is very poor in case of gallium oxide. That is why it is only at the industry level, academic level, rather than industry level. Once you are able to design gallium oxide based devices which has high thermal conductivity, then only it may be used for industry. Although electron saturation is very good in case of gallium oxide, and it is at par with the silicon carbide, but electron mobility and other thing is poor in case of gallium oxide. So another slide that will explain the application of wide bandgap semiconductor material. In case of industrial motor, it is widely used, and it gives higher efficiency. Variable speed device in motors you can achieve using this wide bandgap semiconductor based systems, and fan, compressor, HVAC, all these are using silicon carbide and other wide bandgap semiconductor material for their design. Wide bandgap material are also being used in the data centers, because if you see everywhere, data driven documents are needed. Your whole banking is dependent upon the data driven, and your whole social media, Facebook, as you have seen, they require large number of data for its handling. Even YouTube, etc., all these require large data centers, and for all the power supply that is required at these data centers, they require high wide bandgap semiconductor inverters so as to convert DC electricity. And similarly, for solar and other also purposes, you require wide bandgap semiconductor in the near future. Another graph that will show the application with respect to the frequency. That means if you want to work at 1 to 10 gigahertz frequency, because everyone knows that for working 5G, you need around 3 to 4 gigahertz frequency, and for that RF CMOS can work only when power requirement is less than 1 watt. If you go beyond 1 watt, and if you require high power application, you will have to use silicon carbide or gallium oxide for that purpose. But when you are working for a 5G application, your material will be more suitable gallium nitride based HEMT and gallium nitride based other devices. So this figure will give the application of which type of semiconductor material or bandgap semiconductor material can be used for a specific frequency. So the significance of this study, one can easily see that you can define the role of material for the purposes, and wherever you require high bandwidth, you can design accordingly, or you can design for high power. And material can be a continuous development, because indium gallium nitride is currently after silicon. If second material you are told to choose which material is being used all over the world, it is indium gallium nitride. That means role of gallium nitride is going to be a very important in the. Then the last section of my presentation is related to the future technology. As we were saying that this was the prediction of IRDS, that by 2022 we will be using 7 nanometer. And as you have seen during my presentation today, that day before yesterday, Intel has predicted that they are going to have a 3 nanometer device dimension. Your devices will be of around 3 nanometer. That means whatever is the prediction of IRDS, Intel is going at the same pace. Similarly, you will see the Samsung, TSMC, all these, the pace of the their industry growth is working according to the prediction of IRDS, which was done after 2015 onwards. So the role of projection as well as the industry visage moving ahead, the pace is almost same. These are some of the process innovation that is being used for that means at 90 nanometer you were using strained silicon, then you have gone for high K material and various types of metal gates, and then you, from architecture point of view, you modified your structure, and your instead of double gate you were going for a FinFET and yes, super fins, etc. This was related to the scaling at the book level. What we used to teach to the students are geometrical scaling, and which is being done till 2002, and thereafter we are moving on equivalent scaling from 2003 onwards. And this is not only in the horizontal direction, but it started moving in the vertical direction also, because in the planar design we were more focusing toward the lateral, but this vertical structures that has come into the picture because of the fin, etc. The growth has taken considerably after that also. And lastly, it will be 3D power scaling, which is expected in the future. And if you see the 3D, the growth of the 3D, that will be using gate all around, your structure will be something like this. And some of the fin structure, which is 2D and 3D inverters, which are presented by the industry, and some of the academia who are developing this device and trying to work on it, will have the shape like this. This is basically a growth from the floating body to the fully depleted structure, and thereafter to the 3D growth. The first one, everyone has seen this in your textbooks, that is the traditional bulk MOS, and thereafter you have gone for a partially depleted SOI transistors and then FD-SOI transistors. And from 2003 onwards, when FD-SOI was also not effective, and you started working on the fin, and thereafter gate all around. These are also some of the possible structures that is being used between 2011 to 2022, and some of the structures which are being proposed from 2022 to 2034. And as I have said, that in case of device, nano ribbon is also a chance. At the academia level, it is being presented as an alternative to the FinFET, and maybe in the next few years you will find transistors which will be based on nano ribbons, as expected from the academia. And industry is also working in collaboration with that. This is a heterogeneous, as it has been predicted that the growth is now heterogeneous. It cannot be a homogeneous growth. So your devices will have lot of layers, and 3D structures will be there, so that your device density as well as your system integration will, you will see the growth in it. Similarly, what I have said, that you require large data centers in the coming future. So future industry, if you see the future in electronic industry, you require supercomputers, high and high performance, and quantum computing. Similarly, high speed network will also be needed, because you are moving towards 5G, and maybe in the future it may be 6G, etc. So the growth of fiber optics, and beyond this CMOS, you will have to think, and you will have to plan. Growth of IoT and artificial intelligence, as I have said, they are also being expected, that the coming 5 years or coming 10 years will be the, you will see the era of IoT and artificial intelligence, and therefore most of your devices, whether it is a automobile industry or your medical industry, everywhere you will find the usage of semiconductor. This is a projection of what is going to be from 2010 onwards, when IRDS has promoted. The growth of artificial intelligence is expected to be exponential. And the prediction is that by 2030 it will be more than 350 billion. So this was all about the presentation, and now we should see what our Indian government is doing so as to cope up with the growth of the semiconductor, because till date we are still not having any fab lab that may produce at the 45 nanometer. That means even Chandigarh, which is having the fab lab, and some of the fab labs in the other part of India, you will find it to be 180 nanometer type of length, which was available in the all over the world at around 1998. So so as to cope up with this growth, and now when everyone has seen that the device dimension is not going to go down beyond that, beyond 10 or 12 nanometer, so whatever effort now India will do in the case of fabrication is going to serve the purpose, and most of it will be system based. So the new ecosystem which is desired in India, you require design, design from design perspective, the growth has to take place. So India has taken now a lead in this particular field with the India Semiconductor Mission. And those faculty members who are working, they can submit their proposal, and they can collaborate with the industry also. And in this India Semiconductor Mission, Indian government is going to finance also the work or industry who are interested, or for various dimension. That means I have seen that for if your dimension is less than 90 nanometer, they are going to fund for more than 50%. And if your dimension is of a very high, that means around 12 or 15 at the international level, the sponsor, the Indian government is going to spend more than 75% also on your project. So same semiconductor fab is going to grow in the industry with this mission of Indian government. And the purpose is to not only to grow the simple silicon based devices, but also your LED industry, your TFT industry. So lot of growth is expected in the near future, and for that the proposal of government is there for those who are in the industry, that they can come forward with their proposal, and government can finance also. So we hope that in the near future, in the coming 4 to 5 years, we can see the development of fabrication also in India, and with this Indian government scheme. And that is why everyone should work and hope that semiconductor industry is going to grow. So this was all about brief of what is expected in the semiconductor industry and how it is going to be there in the near future for India as well as all over the world also. So thank you very much.
Okay.
And uh,
Dear
any query
participants,
for discussion?
dear participants, if you have any query or doubts, please unmute your mics and feel free to ask. Is there any query? No. Okay. Thank you very much, sir. I remembered a famous Japanese proverb after attending this session, that is, better than 1,000 days of diligent study is one day with a great teacher. I actually realized it after attending this session as a participant. A very good morning to all the dignitaries and dear participants. On behalf of Electronics Engineering Department of IERT, I, Jitan Kumar Shukla, deem it a great honor and privilege to propose a vote of thanks and to summarize this session delivered by Professor R.K Chauhan, sir. This session is truly informative and fruitful for us because the way sir started and progresses in his talk is truly inspirational and motivational for us as a faculty member, not from academic point of view, but also from the research point of view. Uh, First and foremost, we Electronics Engineering Department of IERT would like to would like to express our heartfelt thank to Professor R.K Chauhan sir, Head and Department of Electronics and Communication Engineering, Madan Mohan Malvi, University of Technology, Gorakhpur, India, for sparing his valuable time for this session. In this session, sir explained the various concepts and research activities going around us in the field of semiconductor device and modeling. He started his talk from Moore's law and he progresses with CMOS scaling and its effect on the performance of devices. He also highlighted the contribution of ITRS, IDRS, and TRS and their objective. He also explained the concept of more than more and more in detail. He also explained the details of devices beyond the semiconductor, CMOS technology, and future carbon nanotubes, carbon ribbons, etc. He also highlighted the importance of semiconductor materials and its effect on the performance of semiconductor devices. He explains wide band gap semiconductor materials for future electronic devices in detail and different advanced structures for future devices for better performance in the field of semiconductor devices. B, as a participants and organizing team, we do not have enough words to express our gratefulness to Professor R.K. Chauhan sir for accepting our invitation and for enlightening us in this session. Thank you very much, sir. We Electronics Engineering Department of IERT remain thankful to the all participants who joined this session to make it successful. I hope all of you get benefited from this session. Once again, thank you all for your kind attention. Thank you.
Okay, thank you.
Good morning, sir. Good morning. Sir, it was really very motivational and informative to all of us. Sir, I am Yogesh. I really listened to it very patiently. Sir, it was really very, very informative and motivational. Thanks, sir.
Thank you, Dr. Yogesh.